The world of classical science is one of simple systems. For example, two magnets sit on a lab table next to each other. Push one, and the other moves in a predictable way. But what if there were 5 or 20 magnets? How would they behave? Would their movements be predictable? It was a matter of faith in the scientific world of the 19th century that if one of the magnets was moved, the movement of all the others was, in principle, predictable. But was it really? In 1903, French mathematician Henri Poincaré set about studying the famous three-body problem, predicting the movement of a simplified solar system consisting of a sun, moon, and earth governed by Newtonian laws of motion. What Poincaré found was that even this simple system behaved in unpredictable ways, and that the three-body problem was unsolvable. Understanding this and other more complex systems, such as Earth's weather, would have to go in another direction. That direction was a new brand of science called chaos theory. A theory whose main premise was that small changes in initial conditions could result in vast differences in the final outcome. Chaos theory remained a curiosity until the advent of high-speed computers and computer modeling in the 1960s. In 1961, Edward Lorenz was modeling the Earth's weather with a computer and found that the smallest change at the 1/1,000,000th of a decimal point could make his predictions useless. He called this result the butterfly effect. In the Amazon, a butterfly flaps its wings, and 2 years later, a thunderstorm appears over Kansas. No flap, no storm. The butterfly effect is everywhere around us. Consider a pile of garbage. Try to imagine all the events that must have occurred to result in just this pile of material. Suppose, for example, that Ray Kroc had never been born and consequently gone on to found McDonald's. In the 1970s, Benoit Mandelbrot added fractals to chaos theory. Fractals are the byproducts, the patterns left behind by dynamically changing systems. Fractals are self-similar as illustrated by these designs. Their inherent property, as with clouds or coastlines, is that no matter how close or far away one gets, the basic pattern is always the same. At the end of the 20th century, the pendulum had come full circle. The long road to the discovery of the simplicity behind the complexity of everyday life had been reversed. Using a computer, one could start with a simple system, such as colored squares on the board that change by simple and known rules. In time, life-like complexes emerged. Self-organizing clusters come into play and interact with each other. Structures are formed that are always on the edge of sudden and radical change. This is, in fact, the way ecosystems, human societies, and even the stock market behaves. Chaotic systems are deterministic, but inherently unpredictable. At the beginning of the 21st century, chaos theory is ripe with philosophical suggestions. But whether it alone or in combination with quantum mechanics will yield new technological advances remains to be seen. The most promising area is perhaps in artificial intelligence. However, chaos theory has the advantage over the other two major branches of the new physics, quantum theory and relativity, in that it seems intuitively correct, reflecting the unpredictability of human behavior.